Hello everyone. Today we will be starting our new topic, that is design of circular water tanks with flexible joint between floor and wall. As per syllabus, we have two different types of design of water tanks. The first one is design of circular water tanks with flexible joint between floor and wall, and the second one is design of water tank as per IS code method. Okay, so we everyone knows that water tanks are used for storage of water. Okay, and these types of water tanks, they may be circular, rectangular, or it may be in spherical shape. Okay, generally the water tanks which are resting on the ground, or the water tanks which are constructed underground, they have generally flat bottom, whereas the water tanks which are having staging or elevated water tanks, they may be having flat or conical bottom depending upon the requirement. Okay, so three different types of water tanks are there. The first one is underground water tank. Okay, the first one is a water tank resting on ground. So if this is your ground level, and if we are constructing a water tank like this, okay, above the ground level, it is considered as a water tank on ground. Okay, whereas if this is our ground level, and if we are constructing a water tank below ground level, okay, it is called as underground water tank. Okay, whereas if we are having our water tank like this and it is supported on some stagings, it is considered as elevated water storage tank or elevated storage reservoir, ESR. Okay, so this is elevated storage reservoir or elevated storage tank. This is water tank on ground, and it is underground water tank. Okay, generally the water tanks on ground, these are used for example, we have sedimentation tank, we have aeration tank, we have filtration tanks. Okay, like this. Whereas the underground water tanks are used for septic tanks or simple water storage tanks also, whereas the elevated or overhead water tanks are generally supported on some staging, and they are generally used for distribution system. Okay, now for construction of any liquid retaining structure, it is to be ensured that the concrete is dense and impervious. Okay, and it is also essential that it should not have some leakage, because if there is some leakage of water or liquid, there will be the serviceability criteria of that particular thing will be, or that particular structure will be not satisfied. Okay, at the same time, if there is some leakage of water or liquid from that particular water tank is taking place, it will undergo some corrosion due to either action of water or some chemical whichever is stored in this particular type of water tank. Okay, okay, so depending upon the placement of water tank, there are three types. The first one is resting on ground, second one is underground, and the third one is a elevated storage tank. Now based on our shape of our water tank, there are four different types of water tanks are there. The first one is a circular water tank. Definitely common sense is it is having circular plan. Second type of water tank is rectangular water tank. It will be having rectangular plan. The third one is spherical, the fourth one is ends, and the fifth one is the water tank having conical bottom. We'll see one by one example of this. Okay, so this is the example of water tank resting on the ground. Okay, you can see here this particular water tank is resting on the ground. Okay, now this is again another example of water tank which is resting on the ground. It is having rectangular or square shape. Okay, you can see here you can see the water tank is provided some depth inside the ground. Okay, so it is an example of underground water tank. Okay, Again here it is an example of underground water tank. We have, this is elevated water storage tank, or this type of water storage tanks are used for distribution systems. That is, water will be lifted to this water tank and then it will be distributed to the households. Now, depending upon the shape of your water tanks, it can be classified as circular, spherical, rectangular, and etc. So this is an example of circular water tank. You can see here the in plan, this particular water tank is having a circular shape. Okay, it is an example of rectangular water tank. It will be having rectangular shape in the plan. Okay, it is an example of the picture shows spherical water tank. Okay, it is elevated water tank which with having spherical reservoir. Okay, you can see here this picture shows the water tank with conical base. Okay, now again, based on the floor base condition, the water tanks can be classified as, the first one is flexible base, the second one is hinged base, and the third one is a fixed base. Okay, now in case of this first flexible base, you can see here some rubber pad is provided like this. Some rubber pad will be provided like this. Okay, and some sealing material will be provided here. Some sealing material will be provided here. Some again one pad will be provided like this. Okay, so in this particular type of water tank, what will happen due to the water pressure? Okay, there will be some water pressure like this. This will be gamma into H. This water pressure will be acting on this particular wall. This is the wall of your water tank. This is the wall of your water tank, and this is the base slab. This is the base slab. So if this is your water tank, okay, if this is your water tank, then okay, I am drawing the elevation only. So these will be your walls, this will be your walls, okay, and this will be your base slab. This will be your base slab. So in this particular type of water tank, will be providing some base, some rubber pads, pads below the wall. Some rubber pads will be provided below the wall. At the same time, some PVC water stopper will be provided to prevent the leakage of water, whereas some sealant will be provided here. Some sealant material will be provided here to prevent the leakage of again water. Okay, so in this type of water tank, you can see here this particular wall, tank wall. Okay, this particular wall will be subjected to water pressure from inside. Okay, the water pressure will be from inside and the pressure will be hoop tension. Okay, now what will happen due to this pressure? Let us consider the pressure is acting like this. Due to this particular pressure, what will happen? This particular wall will be allowed to move slightly with some restrictions. Okay, it will be allowed to move slightly over this rubber pad, over this particular rubber pad which is provided below the wall. Okay, due to which what will happen? There will be no bending stress, no bending moment will be developed in the wall, and only this particular wall will be subjected to hoop tension only. What is hoop tension? If we draw some plan of water tank, then due to water pressure, what will happen? From all the direction, the water pressure will be acting on your wall, and this wall will be subjected to tensile forces, and that particular tensile force is called as hoop tension. It is called as hoop tension. Okay, you have seen this hoop tension in fluid mechanics. Okay, so this is called as flexible base. So what we will be doing? We will be providing some rubber pad below the water tank wall, okay, to prevent development of moment in the wall itself. Okay, then second type of water tank based on the base floor base condition is hinged type of water tank. So what we will be doing? We will be again providing some hinged arrangement like this. Steel reinforcement will be provided and some hinged mechanism will be developed. And the third type is fixed base. So in this type of water tank, all the reinforcement of your wall will be penetrate or will be provided inside the base slab. Okay, it will be provided up to the base slab, and due to which some bending moments will be developed in this wall. So some bending moments will be developed in this particular in this wall. Okay. So as per our syllabus, we will be studying this design of water tank with flexible bases. Now there are a number of water tank IS codes are available for design of water tanks. Okay, which are listed as below. The first one is IS 3370/2009. IS 3370/2009 Part 1. It is the code of practice for concrete structures for storage of liquids. General requirement. We have Part 2 of this particular code. Part 2 is for reinforced concrete structure. Whereas, okay, this should be Part 3. There is some mistake. Okay, this should be Part 3. The Part 3 is for pre-stressed concrete structure. Whereas the Part 4, here we should have Part 4. We should have here Part 4. It is for design tables. Okay, as the design analysis of water tank itself is a very complicated thing, and therefore for making it simple, what this particular IS code IS 3370, I think this year is also wrong. This is, I think, 1967. This year is 1967. Please make this correction. Okay, again here this year is again 1967. Okay, these 2 years are correct, that is 2009. Okay, 2009, and we will be designing as per these IS codes. Okay, for making it simple, some design tables are provided in this IS 3370 1967 Part 4 IS code. Okay. Okay, now what is the design philosophy for design of water tank? Okay, now we know that the water tanks are based on the fact that the concrete for water tank should not undergo any type of crack, or there should not be and the tensile strength of concrete should be within permissible limit, because we don't want any type of cracks in the water tank, because if there are some cracks in the water tank, it will be subjected to leakage. Okay, now in order to control the cracking and various requirements regarding material joints and reinforcement detailings are given in IS 3370 Part 1 2009. Okay, some of them are explained below. The first requirement for water tank is the concrete mix should not be less than M30. Minimum grade of concrete shall be M30 for liquid retaining or for water tanks. Okay, at the same time, use of rich mixes result in less cracking. It will providing rich mixes, that is higher grade of concrete, M30 and above, it will reduce the cracking in the concrete. Concrete, whereas the water retaining structure or liquid retaining structures are subjected to severe exposure condition, where whatever is the location of your project or water tank, it will be considered to be subjected to severe exposure conditions. So based on severe exposure condition, we have to select the grade of concrete and cover to the reinforcement which are provided in IS 456 2000. Okay, now the cement content, not including fly ash and ground granulated blast furnace slag, it should not exceed 400 kg per cubic meter. The cement content, not including fly ash and GGBS, should not exceed this particular limit of 400 kg per cubic meter unless special consideration is taken for increasing the risk of cracking due to drying and shrinkage. Okay, the fourth recommendation for this water tanks is cracking can be controlled by using plasticizer, because if we are using plasticizer, it will result in reduction in the water content, and ultimately it will lead to the less cracking. Okay, the minimum cement content for durability criteria shall be 320 kg per cubic meter. 320 per kg per cubic meter is the minimum cement content for durability criteria of water tanks. Okay, Now cracking can also be controlled by changes in temperature and moisture content at early age of the concrete, and the curing period, minimum curing period, this should be 14 days. The minimum curing period for water tank shall be 14 days. Now at the same time, along with all these requirements, if we provide correct placing of reinforcement bars, at the same time if we use deformed bars, we use bars which are closely spaced, and if we are using small sized bar, it will also result in reduction in the cracking. Okay. Now the crack width for the reinforced concrete member in direct tension and flexure is considered satisfactory if steel stress under service condition does not exceed 130 Newton per mm square, 130 Newton per mm square for HYSD deformed bars. Okay, for high strength deformed bars, the maximum stresses in permissible stresses in steel is 130 Newton per mm square, whereas the maximum surface width of crack, the crack in for tension and flexure should not be more than 0.2 mm with specified cover. So maximum width of crack, it should not be more than 0.2 mm. Okay. So we won't be controlling directly the width of your crack. What we'll be doing, we will be providing some permissible stresses within which the crack will not exceed more than 0.2 mm. Okay. So these were the design philosophy for or requirements for design of water tanks. Okay. Now we'll see what are different methods of design of water tanks. We have two different methods of design of water tanks are there. The first one is limit state method and the second one is working stress method. Okay. So in limit state, we will be satisfying various limit states such as safety and serviceability and collapse. Okay. And it should be the direction should be followed as given in the IS 456-2000. IS 456-2000, the recommendation or guidelines given in IS 456-2000 should be followed for limit state method. Okay. Now for working stress method, okay, the design of water tanks is based on the resistance to cracking and strength. For working stress method, the design of water tank is completely based on the resistance of your concrete to cracking and strength, and various assumptions which are made in this particular working stress method. Okay, these are already covered in your RCC. The first assumption is plane section before bending remains plane after bending. Plane section before bending remains plane after bending. Whereas the second assumption is steel and concrete behave elastically. And the modular ratio M is given by this particular equation. M is equal to 280 divided by 3 sigma CBC. Okay, the third assumption is the tensile stresses in concrete is limited to the values given in, okay, this should be table number 1, IS 3370 part 2. Okay, and the tensile strength of concrete is ignored for all strength calculations. So these are different assumptions for design of water tank by using working stress method. Okay, these are some values of permissible stresses in concrete, okay, which are also given in your IS 3370/2009 part 2 on page number, I think, here we have table 1, permissible concrete stresses in calculation relating to the resistance to cracking. Okay, this is first table. Okay, then we have another table on the next page, that is permissible stresses in concrete, table number 2. Table number 2 is here. Then we have this table number 4, permissible stresses in steel. Okay, these three tables will be required for design of our water tank by water tank. Okay. So same tables are given here. That is the first table number 1, which is given in IS 3370 part 2 on page number 2. It is permissible concrete stresses in calculation related to the resistance to cracking. Okay, these are permissible stresses in concrete for resistance to cracking. So direct tension, these values are given in Newton per mm square for different grades of concrete, and for bending tension or flexural tension some values are given for depending upon the grade of concrete. Okay, now we have some another table number 2, the permissible stresses in concrete for calculation of strength. Okay, now these are the permissible stresses given here. Okay, first we have value of sigma CBC, then we have value of sigma CC. Okay, again value of bond stresses is also given in this particular table. We will see how we have to use this particular table when we design when we will go for actual design. Again, the permissible stresses in steel. Okay, what are the limits for permissible stresses in steel? The resistance to cracking, the permissible stresses in steel is limited by the fact that permissible stresses for resistance to cracking in concrete are not exceeded. Okay, so the value of permissible stresses in steel is given by this particular equation, where sigma ST is permissible tensile stresses in steel, sigma CT is permissible tensile stresses in concrete, and M is the modular ratio. Okay, sorry. This table number 3 shows the values of permissible stresses for steel for strength calculation. Okay, we will be using this HYSD steel bar. We will be using HYSD steel bar. So for this we have tensile stresses in member under direct tension, bending and shear. The value is 130 Newton per mm square, and for compressive stresses in columns subjected to direct loads, it is given as 140 Newton per mm square. So we have to use this particular value of 130 Newton per mm square. Okay, we'll see how we will be using these particular tables when we'll be solving the problems or design. Okay, now IS code recommendation for detailing of water tank. Okay, we know that these types of water tanks are subjected to hoop tension, and it may be subjected to bending moments also. Okay, now our requirement is that the water tank should not leak. Okay, therefore the width of crack is required to be limited. Okay, and also shrinkage cracks, other types of cracks should not be developed after constructions also. Okay, so for limiting that particular, what this IS code has given some recommendation for detailing of water tank. These recommendations are also given in the IS 3370 at part 2 2009 at page number at page number 5. At page number 5 you can see here detailing. Okay, minimum reinforcement. Okay, so these are the different requirement. Okay, I have just listed out that in my PPT also, so we'll see the PPT only. Okay, the minimum reinforcement in the floor and roof in each two direction at right angle within each surface zone. Okay, keep in mind this particular word surface zone, which is shown in figure below, should not be less than 0.35% of the cross section of surface zone of HYSD bars, and 0.64% for mild steel bar. 0.64% for the mild steel bar. So it says that minimum reinforcement in wall and floor in both the directions, it should not be less than 0.35% of cross section for HYSD bars. Okay, but what is the condition? Within each surface zone. Okay, so how these surface zones are decided? Okay, if the depth of your or thickness of your slab, if thickness of, you see this particular figure A, if the thickness of your slab or wall is less than D, the thickness is less than 500 mm. If it is less than 500 mm, then the zone for reinforcement below will be D by 2, the zone for this reinforcement at the below it will be d by 2, and the zone for reinforcement above it will be again remaining d by 2. Okay, so if we have total depth of let us consider 300 mm, then the zone for this particular top reinforcement it will be 150 mm. Okay, the zone thickness will be 150 mm, 150. Okay, d by 2 means 150 mm. Okay, and AST will be 0.35%, that is divided by 100 multiplied by 1000 multiplied by 150. Okay, here the reinforcement will be this much, whereas here again we will have this depth 150 mm again. Okay, so reinforcement will be 0.35%, that is 0.35 divided by 100 into width 1000 meter multiplied by 150 mm. Okay, so this much should be the steel reinforcement provided in the both the directions. Okay, then if we have the thickness of your slab greater than 500 mm, if thickness of your slab is greater than 500 mm, but then we have to go for this particular figure B. Okay, now if thickness is greater than 500 mm, then the thickness of this surface zone will be for this particular top reinforcement, the thickness will be this 250 mm only. Okay, and for bottom reinforcement the thickness will be again this 250 mm, again this 250 mm only. Okay, now the AST here it will be 0.35 divided by 100 multiplied by 1000 multiplied by 250. Okay, this will be the AST. Okay, whereas at the bottom this particular steel, this steel will be again 0.35 divided by 100 multiplied by 1000 multiplied by 250. Okay, so this much mm square of steel is required to be provided. This is the meaning of this particular surface zone word. This is the meaning of this particular surface zone word. Then the second recommendation or for detailing is the minimum reinforcement can further be reduced to 0.24% for deformed bars, and for plain bars for tanks not having any dimension more than 15 meter. The third recommendation is in tank walls and slab having thickness less than 200 mm, the reinforcement can be placed on one face only. It can be provided on one face only if we have depth like this. Okay, and if this particular depth of water tank slab is less than 200 mm, then we can provide at one face, that is at the top. We will have to provide at the top. Okay, then for ground or base slab having thickness less than 300 mm, the reinforcement can be placed on one face as near as possible to the upper surface consistent with the cover. The fifth recommendation is spacing of reinforcement bar. It should not exceed 300 mm or thickness of your section, whichever is less. So spacing of your bar, it should not be anywhere, it should not be less than 300 mm or the thickness of your section. Okay, or thickness of your section, whichever is less. Then the size of bar, distance between the bars and lap and bends, it should be as per IS 456/2000. Okay, now if the depth of your slab base slab is greater than 500 mm, then thickness of that particular member, then each reinforcement face control the half depth. Okay, then each reinforcement, now if the thickness of your slab is less than 300 mm, then this reinforcement will cover d by 2 okay, depth. Okay, whereas if it is between 300 mm to 500 mm, then the top reinforcement will cover, the top reinforcement will cover 200 mm depth, okay, 200 mm depth, that is d by 2, and the bottom reinforcement will be for 100 mm. So while providing the AST, what we have to do, we have to provide here 0.35 divided by 100 multiplied by 1000, and the thickness will be 200 mm here, whereas here the AST will be, here the AST will be again 0.35 into, sorry, divided by 100 into 1000 into 100. Like this we have to provide the steel. Okay, here again if the depth is more than 500 mm, then this will be, the surface zone will be up to this 250 mm from top, and for bottom it will be for only 100 mm. We have to ignore this particular area for calculation of the steel. Okay, now we'll start with our topic, that is design of water tanks resting on ground with flexible base, with flexible base. Now you can see here, now here you can see here, here you can see some joint sealing material is provided. Now you can see here, this is your wall, this is the wall of your water tank, this is the wall of water tank, and this is the base slab of water tank, this is the base slab of water tank. Okay, now add the joint between this wall, add the joint between this wall and the base slab here, add the joint between the wall and base slab here. We can see some rubber pad is provided, some rubber pad is provided. So what this rubber pad will do, due to water pressure, if there is some water pressure from this direction, from inward out, okay, what will happen, this particular wall will be allowed to move slightly away from its original position, away from its original position. Okay, due to which what will happen, no bending moments or no moments are developed in this wall, no moments are developed in this particular wall, and only hoop tension will be developed, only hoop tension will be developed. So this rubber pad will allow the movement of this particular wall. Okay, this rubber pad will allow the movement of this particular wall. Okay, now you can see here some sealing material is provided, some sealing material is provided, just a minute, some sealing material is provided here. Okay, this will prevent the leakage of water from the water tanks. So we will have water like this here, so this particular sealing material will prevent the leakage of water, whereas some strip painting will also be provided here. This will be the strip painting. Okay, it will also prevent the leakage of water. Okay, so this is how these water tanks resting on grounds and flexible with flexible base will work. That is, what will happen, due to this particular pressure from the water, this wall will slide away from its original position, okay, over this particular rubber pad. Okay, and the leakage of water is prevented by this strip painting and the sealing material, the joint sealing material which is provided here, the joint sealing material will be provided here. Okay, also some water bar will be also provided here between this joint, so that will also prevent the leakage of water. Okay, so this is how is the behavior of our water tanks resting on ground with flexible base is there. Okay, no bending moments are developed in this type of water tanks. Okay, as there is no direct joint between this wall and base slab is there, therefore no bending stress moments are developed. In plan, if we see this water tank like this, if we see the water tank like this and it is completely filled with water, what will happen, there will be some tension or force will be acting on the wall like this. Okay, some forces will be acting on the wall like this, which will try to move the wall away, which will try to increase the diameter. Okay, due to this what will happen, some tension will be developed in this particular wall. Okay, like this, some tension will be developed in this particular wall, and this particular tension is called as hoop tension. It is called as hoop tension. Okay, this particular part is already covered in your fluid mechanics. Okay, So hoop tension will be developed in water tanks with flexible base. No bending moments will be developed. Okay. Sorry. Yeah. Here you can see some enlarged view of this particular joint is shown here. Here we will be having, okay, this particular joint. For this particular joint, the enlarged view is shown here like this. Okay. So we have here wall, we have here wall, and we have here base slab. Okay, this particular wall is resting on some rubber pad here. Okay, it is resting on some rubber pad here. Okay, which will allow the movement of this particular wall. At the same time, some sealing material is provided here. You can see some sealing material is provided here. Some sealing compound or sealing material will be provided here. It will prevent the leakage of water. Also some PVC water stopper will be provided like this. It will also prevent the leakage of water. Also some strip painting may also be provided here like this. Strip painting may be provided here like this. Okay, it will also prevent the leakage of water. So here we can have some strip painting. Okay, so okay, due to the pressure from the water like this, this particular wall will be allowed to move away in small amount or small deformation. Okay, so due to this movement, no bending moments are developed in the wall, and only tensile forces or hoop tension will be developed. Okay. Now how we have to design the water tank resting on the ground with flexible base. Okay, now flexible joint is provided between floor and the walls of the water tank, allowing horizontal outward movement of the wall, and hence no moments are developed at the joint. Okay, this is already covered. Now due to this, okay, as no bending moments, no moments are developed, but there is, the water tank is allowed to horizontally or outward movement of the wall. Okay, this horizontal or outward movement of wall is developed due to this hydrostatic pressure which is acting on the walls. This hydrostatic pressure which is acting on the walls, okay, from all the direction, from inside out. Okay, and this hoop tension, the amount of this hoop tension is given by this particular formula. Hoop tension T is equal to gamma h multiplied by d by 2, gamma h divided by d by 2. So this is the equation which is used for calculation of hoop tension which is developing in your walls of your water tank. Okay, the same thing is shown here. You can see this plan of this particular water tank like this. The plan will be there. This will be the elevation. Okay, if we are having some water like this, what will happen? This water will exert pressure on this wall like this, so can be shown like this. Okay, due to this, tension will be developed like this in the wall. Tension will be developed in the wall like this, and the tension will be hoop tension. This tension will be hoop tension. The tension will be hoop tension, and the amount of this or the value of this particular hoop tension, the value of this particular hoop tension is can be calculated by this particular formula. T is equal to gamma h into d by 2, where we have T is equal to hoop tension, gamma is the unit weight of water, that is we have gamma equal to 9.8 or 9.81, d is the diameter of water tank. D is the diameter of water tank. So this is how we will be calculating the hoop tension developed in your water tank. Okay, then the area of steel that will be required for resisting this particular hoop tension in the in your wall of your water tank. Okay, if this is your wall, and it is subjected to, if this is your wall like this wall, it is subjected to some hoop tension T, then the area of steel that is required can be calculated by this particular formula. Okay, by this particular formula we know that we have stress sigma st is equal to hoop tension divided by area of steel resisting it. Okay, we can write this particular equation like this also, that is AST is equal to T divided by sigma ST, where sigma ST is the permissible tensile stresses in steel. And also we know that we have this hoop tension T is equal to gamma h into d by 2. Just put this value of T here in this equation, we get AST is equal to gamma h d divided by 2 into sigma st. Okay, so this is the equation which is used for calculation of area of steel reinforcement required for resisting this particular hoop tension, Okay. Now design of your slab of your water tank, that is also required to be done, because we have two components, that is slab, base slab, and your wall. Okay, we have already seen how we will be calculating the steel reinforcement in the wall. Okay, now the thickness of your tank wall may be calculated from the requirements of tensile stresses in the concrete and should be within permissible limit. Okay, and it should be within the permissible limits. Now we know that this sigma CT, that is tensile stresses in concrete. Okay, this should be greater than this value, that is hoop tension divided by equivalent area or area of transform section. I will explain this in the next slide. I will explain what is this A equivalent. I will explain this A equivalent in the next slide. So this A equivalent can be given by this formula. Okay, otherwise I will explain that first. So what is A equivalent? Okay, so we have this stresses in compressive stresses in tensile stresses in your concrete. It should be greater than T by A equivalent. So what is A equivalent? Now we know that this stress diagram for your concrete is like this, and we consider that this particular portion will be resisting the compression, and we neglect this particular portion. Because we are having assumption that the concrete does not take any tension. Okay, so this particular portion below the neutral axis will be in tension, and hence we neglect this particular portion. Okay, and what we do, the effective area of equivalent of this particular section in terms of concrete will be calculating the equivalent area of this. It will be equal to area of concrete in the compression zone, this area compression zone, and an additional concrete area of MAST, which is corresponding to the area of steel, So what we will be doing, we will be considering the equivalent area is equal to gross area of your concrete plus AG. Let us consider A equivalent, this will be equal to AG plus this will be M minus 1 into area of steel. This is the equation for calculating the value of A equivalent. Okay, so we can write this equation of A equivalent like this also. Okay, so we have this sigma CT, that is tensile stresses in concrete. It should be greater than hoop tension divided by equivalent area. This equivalent area can be written like this, AG plus M by M minus 1 into AST. So this particular equation, this becomes sigma CT, it should be greater than T by AG plus M minus 1 into AST. Okay, now we know that this A gross, this will for your base slab, this A gross, this will be equal to thickness multiplied by A gross, this will be thickness multiplied by width. We will be considering it as 1000. So A gross will be equal to 1000. Therefore this particular equation, this will become like this. Okay, so this particular equation will be transformed into like this, that is okay. So we can write here, for calculation of AST, we will know this particular value, we can calculate this, we can consider this value also, we can know the modular ratio, and hence we can calculate the value of AST from this equation. So we can equate this particular equation. Okay, so this is how we will be able to calculate the base thickness of your base slab. Okay, now what is a freeboard? Now in all water tanks generally we provide about 200 mm of freeboard. Okay, what is freeboard then? If this is your water tank, what we will be doing, we will fill this particular water tank up to this level only, so this particular distance or depth, this is called as freeboard. Okay, we won't fill this particular depth generally, but sometime there may be some condition that water in this particular water tank may be stored up to the full level. Therefore what we do, we will consider the for design purpose we will be considering the water is stored throughout the height of your water tank. Okay, because occasionally there may be possibility that some water may be stored through for full depth of your water tank. So this is the freeboard. Okay, these are some abbreviations given here, that is sigma CT is permissible direct tensile stresses in concrete, sigma BT is the tensile stresses in concrete due to bending, sigma CBC permissible stresses in concrete due to bending, and sigma ST is the permissible stresses in steel. All these abbreviation or these terms are already covered in your RCC, so no further explanation is required, I think. Okay, so we will directly move on to our design of water tank problem. So problem statement is given here, the problem statement is given here. Okay, so this is the problem statement.